The final design project explored how to create a finite state machine that would cycle through a given series of numbers using JK flip-flops and logic gates. This will be done by determining the required input of each JK flip-flop analytically and verifying these inputs by implementing the FSM digitally and physically. I will know whether my analytical work was done correctly if both circuits loop through the given sequence of numbers. The JK inputs were determined by first using an excitation table to create a truth table displaying the given sequence of binary numbers, the sequence of counter numbers needed to handle repeats, and the JK inputs required to transition into the following number. The truth table was then used to create a 6-input K-map for every J and K input for all 6 JK flip-flops. The Boolean expressions for all 12 inputs were determined from these K-maps, except for not K and 2 and not K3, which were able to just be wired to ground. To verify that this process worked, a digital circuit was constructed on multisim by creating the JK inputs calculated analytically using 10 AND gates, 1 OR gate, and the outputs of the 6 JK flip-flops. The Q outputs of the first 4 JK flip-flops were connected to a 7-segment decoder attached to a 7-segment display with resistors. To verify the FSM's resultant sequence, the circuit was run and the 7-segment display was checked to see if it cycled through the intended sequence. And it did! Yay! To further solidify that the digital circuit performs as intended, a digital logic analyzer was used to document the timing diagrams for all 6 Q outputs to verify that they all match the sequence defined in the truth table. And they did! W! Finally, the expressions for each JK input were verified by physically constructing these inputs and connecting them to physical JK flip-flops, whose outputs are connected to a 7-segment decoder attached to a 7-segment display with 1 kilo-ohm resistors. To verify the FSM's resultant sequence, the circuit was run and the 7-segment display was checked to see if it cycled through the expected sequence. And after some debugging, it did! Triple yay! This means that the analytically determined FSM is correct, and both verification methods were conducted properly. The proper conduction of the final design project is very important, as it is a culmination of all the topics covered in the digital circuit section of the class. This includes Carnot mapping and digital logic analysis from topic 6, and sequential logic and finite state machines from topic 7. The complete understanding and successful implementation of this design project is also important on a much larger scale as well, because all the material taught in this section of the course is the base knowledge needed to understand/build every single digital device, from the more intricate and complicated devices like phones, laptops, and TVs, to simpler devices such as a digital clock.